Swayam Prabha. Digital India. Educated India.
So how is your projects going? How are your projects going?
Started yesterday.
Have you all started?
Yes, it started yesterday.
You've all met your mentors at least once?
Yes.
Taken instructions from him or her?
Done.
Okay. When is the next project session? The afternoon after lunch?
Yeah, it
Today?
starts in the afternoon.
Okay. All right. So what I want to talk about today is a couple of things I mentioned earlier but didn't have time to complete. The first one was the tiling problem, and the second one is the Stirling formula for factorial n. I'd like to talk about those today, unless you have something more urgent to ask, in which case do so right now. Or at the end, whichever way. Okay. So let's quickly knock off this tiling problem, the question of tiling a floor, an infinite flat floor, with polygonal tiles, given size and given shape. Okay. And the statement was that the only regular tilings you have on the plane are with equilateral triangles or squares or regular hexagons. Nothing else is possible. We'd like to establish this rigorously. The way you do it is as follows. So if you took, for example, hexagonal tiling, and these shapes, you tile the entire floor with these shapes, etc., etc., then it's clear that regular tiling will occur if you take p-sided polygons Let's suppose that the regular polygon has p sides and p, the least value is 3. You have equilateral triangles, and then you have 4, 5, 6, 7, and 8, etc., etc. And let's put them round a vertex without overlap or without gaps. And let's suppose there are q polygons around each vertex. So I call this point a vertex. And clearly there will be 3, this tiling will go like this. Etc. So around this vertex there is 1, 2 and 3 polygons. So I'll assume that there are q polygons around each vertex. If you take the example of the square tiling on the floor here, there are 4 polygons, 4 squares around each vertex. So q is 4 and p is also equal to 4 because it's the number of sides of a square. So I'm going to look at p-sided polygons, q around a vertex. This immediately implies that q times q polygons times theta p, which is the internal angle of a polygon. This is the internal angle of a polygon of p sides. This must be equal to 2 pi. That's the condition you need for no gaps and no overlaps. Neither of them is allowed. Q times theta p must be exactly equal to 2 pi. Okay? And that gives you an exact tiling. The question is, what's the internal angle of a polygon of p sides? The external angle is easy to find, because the external angle of this is the, if you take this polygon for example, this is the external angle here. What's that equal to? So take a polygon, for instance this. You come here this way, and then this is the external angle, you go here, this is the external angle, you go here, and this is the external angle, then this is the external angle. So you have p external angles which make 2 pi. You walk around this polygon once, you finish one circuit. So it immediately implies that theta p equal to pi minus 2 pi over p. Because the external angle multiplied by p is equal to 2 pi. And the internal angle is pi minus the external angle. So this is your condition. Right? Put that in here and you get q times that's the condition. This condition gives you p comma q tiling. p-sided polygons, q round a vertex. And what does that simplify to? Yeah, the pi cancels out on both sides, and then you're left with something which easily reduces to 1 over p plus 1 over q equal to 1 over q. That's the condition for an exact tiling. And if this condition is met by a pair of numbers p and q, I'll call it pq. P comma q tiling. What's the least value of p? 3. And what's the least value of q? Least value. Also 3. Also 3, right? Not 2. 2 is not possible. 2 doesn't give you a polygon. So we need to know what are the solutions of this equation where pq equal to 3, 4, 5. What are the possible solutions? You must solve in integers and this condition must be met. That's our square tiling on the floor. 1/4 plus 1/4 is equal to half, right? But it's also clear that p equal to 3, q equal to 6 is a solution. 1/3 plus 1/6 is a half. So you can have triangles 6 round a vertex. Equilateral triangles of 60 degrees. 6 round a vertex gives you 360 degrees. So that's a possibility. So this is tiling with triangles. This is with squares. What else is possible? Pardon me? What would that correspond to in terms of p and q? P equal to 6 and q equal to 3. This condition already tells you that if p comma q is a solution, q comma p is also a solution. They are dual of each other. They are duals of each other. The square tiling is a self-dual tiling. It's its own dual. Right? When I say dual, what I mean is the following. If you took a lattice, a square lattice for instance, etc., infinite square lattice, I replaced each tile, each face with a point at the center and form a dual lattice from these. That is also a square lattice. So the square lattice is self-dual. P and Q must be symmetric, must be the same value. Is any other solution possible? Nothing else is possible. You increase P and Q, this whole thing becomes smaller than a half. Becomes less than a half. So you can't get those solutions. And since P and Q can only take values from 3 upwards, these are the only solutions possible. Now suppose I come along and say I want to do this on the surface of a sphere, which is a curved space. What are the possible tiling with regular polygons? By a polygon I would mean a spherical polygon, for instance, if you took a surface of a sphere. Okay. For that, yeah, I'll do that right now. Yeah. So for that we'll take a sphere which is a surface of positive constant curvature. First let me tell you what's the concept of a curvature. Have you heard of Gaussian curvature?
Yes.
You know what Gaussian curvature is, right? So let's draw a picture and see what it looks like. If you have a curved surface of some kind, on this curved surface you can have a set of axes, perpendicular axes at any point, and when you have a normal curve like that, at any point you can define a tangent, you can also define a curvature, because you fill the curvature of this circle to this. So this is called the circle of curvature. At every point, in addition to a tangent at every smooth point, you can also have a circle of curvature which kind of touches this the line that you have, right? The radius of that, this is called the circle of curvature, and this is called the radius of curvature. It's clear that on a surface you will have two such things. You will have one curvature like that and another curvature like this, at right angles to each other. Okay? If those radii of curvature are R1 and R2, then 1 over R1, R2 is the Gaussian curvature. What is it in a sphere? Imagine a sphere. Imagine the equator, for instance. That's a circle of curvature on the surface. The longitude, prime longitude, is another circle of curvature, and they are at right angles to each other, and they have the same value. So what's the Gaussian curvature of a sphere of radius r? 1 over r squared. That's positive. But it's also possible to have this Gaussian curvature negative. When you have one curvature in one direction, one side of the surface, and the other curvature circle on the other side of the surface. For instance, a point like this. Let me see, I'm not very good at drawing, but we took a point like this, for instance. There's one circle of curvature like this and a perpendicular circle of curvature like this on different sides. This is a saddle point, like the middle point of a saddle. It's got curvature on one side, the circle of curvature is on one side of the surface, and the other circle of curvature is on the opposite side of the surface. So one of them has a positive sign and the other has a negative sign. The product is negative, right? Now, just as a sphere is a surface of positive curvature, constant positive curvature, at all points the curvature is exactly the same. Similarly, you can imagine a surface of negative curvature, constant negative curvature, of which we can only represent one point here, because at other points this is no longer true necessarily. To represent an infinite surface of negative constant curvature, I need 4 dimensions in Euclidean space. Only then can I embed such a surface in Euclidean space. So we imagine it, we know all its properties, but we can't draw it, except in imperfect pictures like this. Right? We'll come back to this. These spaces are called hyperbolic spaces. We'll come back to that. Right? Now let's ask, how many ways can you tile a surface of constant positive curvature, namely a sphere? Yeah? Is actually?
So, we talk about like hyperbolic curvature and then the Poincare disk.
The Poincare?
Disk on where the edges of the circle are infinitely covered.
No, I didn't understand. What did you say?
No. In the sense, for you, right now you showed us that saddle shaped thing with negative curvature that we call hyperbolic geometry.
Yeah.
Isn't there like one representation? I think it's called the Poincare disk model.
Yes, it's called the Poincare disk model. There's a half plane model and there's a disk model.
Yeah, where like in the edge of the circle is infinitely covered.
Yeah.
So we can use that as a representation.
Sure, yeah, we know all about the constant negative curvature spaces. We have 2 or 3 models for it. We can use them to do all the results rigorously.
Not like actually.
Well, topology is you don't need necessarily to be able to visualize things in 3-dimensional space. Okay? There are a lot of surfaces which are 2-dimensional objects which cannot be embedded in 3-dimensional Euclidean space. You need at least 4 dimensions. There's a theorem which says the following: if you are given an n-dimensional manifold of some kind, some properties, you need at best 2n Euclidean dimensions in which you can embed this surface, this manifold. So if you take surfaces of dimensions 2, there will be a lot of surfaces which cannot be embedded in 3-dimensional Euclidean space, but you're guaranteed that every one of them is embeddable in 4-dimensional Euclidean space. But you can have models of it using a different metric on two-dimensional surfaces itself, like the disk model or the half disk model, etc., half plane model, etc. We can write down all its properties. We'll come back to negative constant, negative curvature in tiling. Right? So let's look at tiling on a positive curvature. Yeah.
How would you define what negative curvature is? Because
Oh, you want me to write down the exact formula for this? I'm not going to do that here. I'm saying this in physical terms. You have a surface, and on one side of it you have one circle of curvature, the other circle of curvature is on the other side of it. That gives you a relative minus sign between them.
that's relatively speaking,
That's right.
they are on opposite
Yeah,
sides.
there's no rigorous convention about which one should be positive, which one should be negative. Any more than there is a convention says the proton is positively charged, the electron is negatively charged.
So wouldn't we be able to say a sphere has constant negative curvature?
No, you don't want to say that because we know how to define a sphere's curvature, right? We know the two principal radii of curvature stay on the same side of the surface, the centers of curvature.
Okay.
In this case, we define positive and negative curvature.
We could have started by defining all the real numbers to be actually purely imaginary and all the imaginary numbers to be purely real. We could have done that.
Yes.
Matter of convention, right? So it doesn't matter. Okay. So let's restrict ourselves to normal spheres. It's called S3. So let me. S2. This is the surface which is most easily visualized by saying x squared plus y squared plus z squared equal to 1 in three-dimensional Euclidean space. So I start with in R3. Consider x squared plus y squared plus z squared is 1. It's the unit sphere in two dimensions, right? The two-dimensional surface. Okay. And that's the equator. The fact that you can embed it in three-dimensional space tells you that you can see a balloon. But you don't need that representation. You don't need to be able to see it to deduce all its properties. Now I'm going to ask, what are the ways of tiling this thing with regular polygons, of spherical polygons, so to speak. Okay. For that I have to define for you the distance between 2 points. What's the definition of the distance between 2 points on the sphere? I define it by saying here's a point, here's a point. There's a great circle that passes through these 2 points and the center of the sphere. There's a great circle which passes through, and that will be your definition of the distance between the two. On any 2 points on the sphere, take a great circle distance. The great circle is the circle passing through both these points as well as the center. The plane of the circle has the center of the sphere in it. That defines for you the shortest distance between these 2 points. It also defines for you the longest distance, because the longest distance is in the other direction. Okay? So we have a definition of distance. Now we need the notion of a triangle. So what's the next step? The next step is to say that if here's my sphere with this equator, I can form a triangle like this by taking this to be a geodesic, namely the shortest distance between these 2 points, this between these 2 points and this between these 2 points. I join these three and I get a spherical triangle. Okay. What is the sum of the angles of this spherical triangle? It's always greater than 180 degrees, always. Because it can go, what's the largest it can be? It can be quite large. For instance, if I start at the North Pole and I come to the equator by a longitude and I go here and go back along a longitude like that, each of these is 90 degrees. I go from the North Pole to the equator directly south and then go eastward, directly eastward, which is at 90 degrees, and go northwards again. I'm back on the North Pole. And I've gone through 3 right angles, so 270 degrees. That's the sum of the internal angles of a triangle to this triangle. If I took a smaller triangle or a bigger triangle, I get a bigger angle. If I take a smaller triangle, I get a smaller angle. For instance, if I took this angle is less than 90 degrees, this angle is 90, this is 90. The answer is still greater than 180 degrees, but smaller than 270 degrees. So you easily see that the sum of the three angles of a spherical triangle is always greater than 180 degrees, but it tends to 180 degrees as the area of this triangle will become smaller and smaller. Unlike Euclidean geometry, where the sum of the angles of a triangle is always 180 degrees, independent of the size of the triangle, on a sphere, the sum of the three angles depends on the size of the sphere. Can be as large as 270 degrees, can be as small as 180 degrees. When you come to an infinitesimal triangle, it becomes 180 degrees, because that infinitesimal triangle you can define on a tangent plane, and that's 180 degrees. Right? So is this clear? Now once I have defined the triangle, I can define other polygons, regular polygons on it. But this internal angle is going to be bigger than what it is in the Euclidean case, pi minus 2 pi over 2. So we have an equation now for the tilings, which says, one second, q times theta p is equal to 2 pi. That condition has still got to be met, because you don't want overlaps and you don't want gaps. Yeah, somebody had a question?
Sir, if we were to draw a triangle like this in a four-dimensional circle, then how will that impact the angles? Like, how are the dimensions impacting the maximum angles that can be enclosed in a triangle?
A triangle is always a planar surface, right?
Yes, sir.
We defined it as a plane.
Yeah.
So I didn't understand.
Like with the three-dimensional spheres,
The three-dimensional sphere, the x squared plus y squared plus z squared equal to 1, was merely a crutch for me to envision this surface.
like, sir, when we're drawing the triangle, we get 270 as the maximum internal sum of the
It could be larger than that. What if I did this? What if I went from here to here, went like this, and then went back? That's larger than 270 degrees.
So how do the dimensions actually impact the internal angles of the shapes?
It's not that the dimensions impact it. What do you mean by dimensions impact this?
How is it that this in not being two-dimensional the sum of internal angles of the triangle?
Every triangle is equal. On S2, every triangle is two-dimensional.
But the sum of the internal angles here is less than
Okay. You want to know what's the relation between the size of the triangle and the lead or lag angle. Is that what you're saying?
Yes, sir.
I'm not sure
The
what.
dimension and the size of the yes, sir.
That involves something called parallel transport. I don't want to get into that right now. We will talk about this.
Yes.
Okay? The idea is that, you see, in Euclidean space, we got brainwashed. We got used to to the fact that you can actually translate geometry from one place to another. For instance, if I drew a line like this on this plane of this blackboard and another line like this, how do I tell that they are parallel to each other? How do I tell that they are parallel to each other?
They want to do something.
I can transport geometry from one place to another. What I can do is to do the following. I put a coordinate axis here, xy axis here, and I rigidly transport that till I come here. And if it makes the same angle, I say these two lines are parallel to each other. I have done parallel transport of my coordinate frame from one place to another. You try doing that on a spherical surface, your geometry will twist your axis without your knowing it. Look at what happens here. I start at this point and I carry this geometry with me. By the time I move to this point is moving inwards, pointing inwards, and this guy is pointing upwards like this. I have to allow for the fact that the space is twisted or curved under me. So I have to define the notion of a parallel transport. I have to tell you what I mean by translating a coordinate system parallel to each other itself. The way you do it is, you move along a geodesic, making the axis perform a constant angle with the geodesic. That's parallel transport. It takes into account the curvature. Then you can compare geometries. So you need that concept of parallel transport, which is a fundamental concept in curved spaces, before you can compare geometries at different places. Okay? So that takes care of the kind of question you have.
draw a polygon on a sphere, can the other angles also exceed 2 pi, or do we just take the
We are talking about regular polygons, right?
Yes.
We're talking about regular polygons. So let's see what happens. That's exactly what I'm getting to. Now let's see what happens. This is still the same condition. This is still the same condition, right? So it says theta p equal to 2 pi over q. But theta p must be bigger than pi minus 2 pi over p. Because this is a Euclidean value. The internal angle on a surface of positive constant curvature must be greater than what it is in Euclidean space. Whether it's a triangle or any other polygon, it doesn't matter, it's puffed up. What does this condition tell you? So again, same way, you cancel the pi and it says 1 over p plus 1 over q is greater than a half. That must be strictly true.
When you talked about defining parallel lines parallel, then you can rigidly transport them over the other by assigning them the same coordinate axis. So isn't it we need to know what parallel lines are to define coordinate axes, because parallel and perpendicular things are interrelated. You see, coordinate axes are orthogonal.
Well, I don't need coordinate axes. I take a vector on the space and the vector must make a constant angle with the geodesic as I move along. Then the vector is parallel transported. That's all I need. That's all I need. I don't need it. Yeah. Okay. So this condition has to be satisfied for regular tiling on the surface of S2 or surface of constant positive curvature. Right? What are the possibilities? These were the Euclidean possibilities. Now we are looking at the spherical possibilities. How about p equal to 3? Q equal to 3. P equal to? How can a polygon have just two sides?
So, we can have the part from one pole to the other pole, and then another great surface from one pole, on a sphere, from one pole to another. That's how when we draw lines of longitude.
A regular polygon? How will it be a regular polygon? How can it be a polygon?
Because they are straight lines, and then the two angles are the same.
Not tell the spaces.
Lines of longitude.
Yeah, but it will be like this.
Yeah.
Space will be.
That space is another shape.
Not tell the same shape. No, but the question is that even a polygon?
It's not a polygon.
How is it
Why is it a polygon?
because it's made of a part of a great circle, and it's because it is a closed curve, and then the great circle, you can say they cover the line segments that we talk about this cover the same distance, because the distance from the two equator we can say is the same, right?
So how do you define a polygon?
Yeah, and then
P greater than or equal to 3.
Sir, but I can't explain it. Can I draw it?
I know what you're saying. You're taking two lines of longitude. You're saying take two lines of longitude and call them a polygon. Call it a polygon.
So you're saying take the two vertices of the polygon to be the poles,
Yeah.
and then you draw two great circles joining both, and you get a closed curve, and that's a polygon. But two
The
vertices.
angles are the same.
Two
The
sides.
distances are also the same. And it's close also.
You're asking why can't orange like in,
Why is the shape formed by two intersecting lines and how do you not?
So you're asking like this sort of a shape.
Yeah, like see like those patterns that you used to make glue, they have that shape.
Yeah, like,
come on, come on. Why is that a polygon?
So because, as you said,
The
angles are
distance,
equal. I mean,
yeah, the
like this
angle.
angle would be equal to this one, then it's like straight lines on this way.
It's made of only straight lines because
it's
they're
a
part.
closed curve.
It's made of only straight lines because they're part of great circle,
Mhm.
and it's a closed curve. And then we say these two angles are the same. So why is it not correct?
Call that a polygon, I don't understand.
So, okay, like, I think it's a fundamental misunderstanding of us about what a polygon even is.
Yeah.
Let me start by defining it with p greater than or equal to 3. Okay? Then we'll come back to these anomalous cases we're talking about. Okay? Like the generalization of a triangle, etc. We'll come back to this other question. I see what you're saying. You're saying like orange, like on an orange you have these little, calling that a tiling. Okay. We'll come back to that. I don't, let's address that a little later. Okay. Okay. So is P equal to 3, Q equal to 3 allowed? Certainly when the sum of the two is 2/3, it's certainly greater than half, it's allowed, right? What else is allowed? So this is with triangles. What else is allowed? One over P plus 1 over Q must be greater than half.
So it can be P is 3, Q is equal to 2 also.
So how about this? Is this allowed? Certainly bigger than half, right? The moment you allow a PQ, QP must also be allowed because it's a symmetric condition. So this is also allowed. What else is allowed? How about 3 and 5? 1/3 plus 1/5, is that allowed? Comes to 8 over 15, which is certainly bigger than half. Is anything else allowed? Is anything else allowed? The moment you increase P and Q, the sum 1 over P becomes smaller, 1 over Q becomes smaller, it can't exceed a half. So this exhausts everything. This actually exhausts all the possible tilings. Here you're tiling with triangles, equilateral triangles on the sphere. Here with equilateral squares, with normal squares, spherical squares on the triangle, on the circle. And here triangles but 4 rounder vertex. These are triangles with 5 rounder vertex. Triangles with 5 rounder vertex, we can intuitively see why that is going to happen. Because if you took a plane and you tiled it with equilateral triangles, you need 6 of them around a vertex. Remember that was the solution, 3, 6. That looked like this. That looked very much like this. Just ignore it. You can't even refuse this call. Thank you. So you have 6 of them around a vertex on a plane. Now suppose you imagine cutting off one of these guys. Cut this and join the two together. Imagine doing this with paper. You have a triangle, 6 triangles, equilateral triangles meeting at a vertex, and you cut off one of the sectors, one of the triangles, and bring the two joints together and bring it up and stick it together. What happens to this object? It pops up and becomes a cap, right? With 5 triangles around the vertex. And you do 5 on top, 5 below, and put 10 triangles at up and down in between, and you get a 20-sided figure called the icosahedron. That's a regular solid, perfect solid, right? So that's where this tiling comes from. When P equal to 5, Q equal to 3 corresponds to putting 3 pentagons together at each vertex. Again, curved surface, it gives you 12-sided figure, faced figure called icosahedron, called the dodecahedron. And they are duals of each other. So these two are duals of each other. These two are duals of each other. What does P equal to 4, Q equal to 3 actually look like in the solid case? What I'm imagining is the following. If you have, for instance, if you have a equilateral triangle on us and you circumscribe with a triangle, on S1, this is a tiling. That's a tiling. That's a tiling. But then the moment I go to a Euclidean plane, I can look at the chordal distance here, here and here, and I get a regular polygon. Similarly, I can take an equilateral, I can take a tiling on the sphere and look at the chordal distances now between neighboring vertices. That will give me a solid which is a perfect solid. One kind of polygon, the same face, tile repeated over and over again in order to give you a solid which is a perfect solid made of regular polygons. And there are only 5 possibilities. They are called the Platonic solids. These are the only 5 possibilities. What does this correspond to? What kind of solid object is it? You have triangles and you must have 3 around a vertex.
So we can have a triangle and 2 around a vertex.
How?
So what I would do is something along the lines you were saying. When you have one of the points at the vertex, and the other 2 points on the equator, then you get a 180 degree. One of the angles will be 180 degrees. And then
That's a degenerate case.
Huh?
An angle of 180 degrees is a degenerate case. It's one line. It's not a corner, it's one line. Okay. So what does P equal to 3, Q equal to 3 correspond to? In terms of perfect solids. Have you heard of a tetrahedron? That's exactly what it is, because a tetrahedron looks like this. There's 4 faces, so 4 triangles. Around each vertex there are 3 of these guys. So P is 3 because they are triangles, and P equal to Q equal to 3 because there are 3 around each vertex. What does this correspond to? P equal to 4. No. P is 4. How about a cube? P is 4 means it must be a square, each face must be a square. And each corner of a square has 3 of these squares departing in 3 orthogonal directions from it. So this is just a cube. What does P equal to 3, Q equal to 4 mean? That's an octahedron. You have 2 pyramids, square pyramids, one on top of each other in opposite directions. So it has 8 faces, each of them is a triangle, and there are 4 around each vertex. Q equal to 4. This, as we saw, is, so this is an octahedron. This is a Yeah, this is an icosahedron. They are the only possibilities in 3 dimensions. By the way, you can extend this classification to higher dimensions and ask how many perfect solids are there solid. They're called polytopes in higher dimensions like 4, 5, 6, etc. The number increases very rapidly. Now we come to the case of negative curvature. Suppose you had a surface of constant negative curvature, which we can't write in 3-dimensional Euclidean space. In how many ways can you tile it? But you can extend exactly the argument I gave earlier, because now the triangles would start looking like this. Instead of being bloated outwards, they're being sort of shrunk inwards this way. And exactly the same condition as the earlier ones would apply, except that theta p is now less than pi times the same condition as above will now tell you that 1 over p plus 1 over q is less than half on a surface of constant negative curvature. How many solutions are there for this?
Are there infinitely many?
There are infinitely many possibilities. Any regular polygon will serve tiles. Infinite number of possibilities. So you see immediately how strong the curvature condition is.
When we talked about positive curvature in 3 dimensions, we first, is there anything like positive curvature in 4 dimensions? In the sense that, is there a radius of curvature that talks about a sphere instead of a circle?
You're asking, is the curvature can it be generalized to arbitrary dimensions? Yes.
So if
Yes.
we have something like a spherical curvature in 4 dimensions, positive curvature, is there any pattern to the number of shapes that we can?
When you say in 4 dimensions, are you talking about a 4-dimensional space, or are you talking about a space embedded in 4 Euclidean dimensions?
3-dimensional space embedded in 4 dimensions.
All right. Okay.
That somehow has the properties that are like a sphere.
Yes.
Yeah.
Yes, it is. It is there. Let me show you how this works. A little bit of imagination is needed. That's a very good question. Let's see how this goes. Let's start with one lower dimension and I'll show you how S2 is built up from S1. So I start from the following. I start with a circle. This is the normal circle which we draw in 2 Euclidean dimensions on the plane of the blackboard, right? S1. It corresponds to saying x squared plus y squared equal to constant in 2-dimensional Euclidean space. That gives you a constrained 1-dimensional object called S1, which is just a circle. Okay? Now I take 2 of these circles. So I take a circle here and make it into, I distort it topologically, you can distort it into a spherical cap. And I take another guy here and distort it into a spherical cap. So I include the space in between, inside this S2, inside that S2, and make 2 balls out of it. The original S1 was here and this one, the other guy was here. I bring the 2 together and I identify points, pairs of points. So I identify this point with this point, this point with this point, this point with this point, and so on. I identify them. They are mathematically taken to be equivalent points, exactly the same point. That's like saying I take these 2 circles and stick them together and I get S2.
When we have S2 from S1, is there S0?
S0 is just a set of 2 points. That's a good question. How do you define a circle, by the way? The locus of all points equidistant from a given point on a plane.
So can we define this S2 sphere as like an extension, like for a circle we define as set of all points?
Yeah, the problem with S1 is that it's not an interval, it's just a set of 2 isolated points.
Yeah, but instead, can we take for the circle a diameter and can we say all the circles that
Yeah, a lot of manipulations can be done, but S0 is just a disjoint number of points, it's just 2 points.
yeah, but
From the origin, if I say there's only one direction, one dimension, so that's the R1. And now I say I look at points equidistant from the origin. 2 points equidistant from the origin, they're just a set of 2 points.
because when we talk about the set of all points that are equidistant from a central point, and then we say they're just like like as I said, they're just disjointed set of points that creates a circle. In this case, we can also define the sphere as a disjointed set of circles that share one singular diameter.
Yeah, but what's the gain? What's gained by that?
I mean, because so that it follows from our definition of the circle to a definition of sphere.
But S0 has distinctly different characteristic from S1, S2, S3 and so on. Distinctly different characteristic. It's just a disjoint set of points. So it's got very different topology from anything else. Okay. So let me come to where S3 comes from, where you get S3 from. So this gives you So he started with a pair of, this is S1, this one was another S1, and I glued the two together and got S2. Now imagine, which is difficult to imagine, two spheres, the surfaces of two balloons, and identify corresponding points by sticking them together. You can't do that in 3 Euclidean dimensions, you need 4. That's S3. But all its properties are completely defined.
So for that, we have to, like we did for S1, we have to like slice the sphere someday.
You have to identify points with invisible strings, if you like. So you've got to take one S2 here, another S2 here, and identify pairs of points with invisible strings. So the manifold looks very completely smooth, exactly like S2, a little more intricate than S2, but it's not, you can't visualize it in 3 Euclidean dimensions.
So can we say that like for our S2 sphere, we have an equator that's a circle where we identified all the points. So for the 4-dimensional space, we have a sphere that where all things are.
Yes. Yes. Oh yes, yes. A solid sphere. Yes, indeed. Indeed. Yes, of course, I have to do that immediately. Just as here I did that and these are all points of the manifold. Similarly, here I have to imagine now a solid sphere, the surface is S2, and identify all pairs of points on the surface, on the two surfaces. That's S3. And the famous Poincare conjecture, which stood until a few years ago, was that the only simply connected compact 3-dimensional manifold is S3. Everything is topologically equivalent to it. That's been proven now.
So this is specific about the Poincare conjecture.
What should I say about the Poincare?
So there is divine compactness for
The
us.
word that you said, UI.
The only compact, now there are a lot of terms like compact and so on which I am using which are not defined. The only simply connected compact 3-dimensional manifold is S3. It is topologically equivalent to S3. Nothing else exists.
What is compact in?
Bounded and closed. That means it's bounded. All the points are about finite distance. And they're closed. In other words, all limit points are part of the set.
Oh, right. I remember some place I heard that I think I heard this for draw any arbitrary shape on the boundary of that set, some part will be outside, some part will be inside. Does that have something to do with compactness? Or does that have
No, compactness simply means that all points are finite distance, if you like, in some, nothing goes to infinity. And closed means all limit points are also part of the same set, including boundary points, etc. And simply connected means you can go from any point of the space to any other point by a set of arcs which don't go outside the space. And simply connected means that such a closed loop, when you come back, can be shrunk to a point without leaving the space. Okay. Is S2 simply connected?
So, could you repeat the last slide? I said to be shrunk down to a point without.
Can be shrunk down to a point by a smooth deformation without leaving the space. Is S1 connected? Can you go from any point of a circle to any other point without leaving the circle? Yes, you can. Is S1 simply wait, before we come to that. Is S2 simply connected? Is S2 connected? You can go from any point of the globe to any other point, right? Is it simply connected? I take any closed path on this sphere, can I shrink it to a point without leaving the sphere? Yes, you can. It's simply connected. Is S1 simply connected? S1, the simple circle. It is not simply connected. That's very, very crucial. Because imagine a rubber band going around this rim of a cycle tire. That's the cover of S1 with another S1, right? Can you shrink that rubber band to a point without leaving the sphere? Without cutting it? Not possible. Right? You can go all the way around 3/4 of the way and go back. That path can be shrunk to a point. But if you go all the way around 360 degrees, you can't shrink that to a point without leaving the sphere, leaving the circle. Then you can go around twice, and that cannot be made equivalent to going around once. Then you can go around 3 times. You could have gone in the opposite direction. So it's clear it's infinitely connected space whose connectivity is defined by an integer, the set of integers. That's called the first homotopic group of this sphere, of this circle, etc.
So if we consider a circle along with all the interior points, it would be simply connected.
That's a disk. Now he's saying let's take a circle with all the interior points. Circle with all the interior points. That's a disk now, right? So x squared plus y squared is less than equal to 1. Is this space connected?
Yes.
It's connected. You can go from any point to any point without leaving the surface, without leaving the space. Is it simply connected?
We could take this one point and
Like if you deform it to make the path goes to the point. So, but then why is this sphere?
Is it simply connected?
Oh, wait.
Can I take this and shrink it to a point? Can I take this and shrink it to a point, this path? Yes, indeed you can. You can shrink it inwards. So it's simply connected, right? And connected. Is this simply connected? A disk in which this point is left out. So it's a disk in which it's called the punctured disk. I punctured it by putting a hole there. Is that a simply connected space? The punctured disk. Is it connected?
yes, yes.
Yes. Is it simply connected?
No, sir.
What if I took a path like this? Can I shrink that to a point without leaving the space?
It's leave a little gap for the point.
The origin is not a part of the space. It's punctured. So the particular point O is not in the space. Is it simply connected? It's clear it's not, because anything that circles this point immediately is not a kind of shrinkable to a point. This is topologically equivalent to S1 itself. Right? How about this? The two torus. The rubber tube. Inflated rubber tube. This is called the two torus because there is the torus S1 here and an S1 in the other direction. Right? And it's denoted by T2. It's formed by saying take a circle And on each point of the circle you put a perpendicular circle. You attach a perpendicular circle in all around and you get a torus, two torus. Is it simply connected?
Then on the surface of the two,
S1 itself is not simply connected. So S1 cross S1 certainly is not simply connected. You can have any infinite number of distinct closed paths on this surface without leaving the space. You can go around this larger circle many times, you can go around the other one many times, you can mix the two, etc., etc. You can define higher dimensional tori, S1 cross S1 cross S1, etc., etc. Okay. What did I want to say? So all the surfaces Sn, S superscript n, are all simply connected except S1, which is infinitely connected. And you can construct the higher S's by gluing together the lower S's. Actually, it turns out that the subject of topology is absolutely fascinating. Turns out that if you increase the number of dimensions like 4, 5, 6, etc., matters become simpler, become easier. If you go to S1, it's completely trivial. It's very easy to understand. S1, S2, and so on. Paradoxically, it turns out, that's the way it turns out, the universe turns out, 3 and 4 dimensions seem to be the most interesting physical dimensions of all. We live in 3. But if you include space-time, it's 4. So it looks like 3 and 4 dimensions, the dimensionality is high enough to have a lot of interesting possibilities, but low enough that these possibilities are non-trivial. For instance, if you have knots cannot be done in 4 dimensions. You can undo the knot. But in 3 dimensions, you have an infinite variety of knots. So for some reason, there's this dynamic tension which makes 3 dimensions a very special dimensionality.
First, can we define a knot as like some line, as in
Yeah, there's a precise mathematical definition of knots.
yeah, so it's using a line, we define a knot using a line.
Yeah, knots are always one-dimensional objects.
Yeah, so then knots are the one-dimensional shape embedded in a three-dimensional
Yeah,
space.
yeah, but we know the difference between a knotted closed circle, loop and an unknotted one. So you can classify all these knots.
Sir, how would you even prove that a knot cannot exist in 4 dimensions?
Let me show you one way in which you can not prove, there are rigorous proofs for this, but let me tell you the physical example of why 3 and 4 dimensions are special. Why 4 dimensions is easier than 3 in some sense. If you took a random walker in 3-dimensional space, right? Random jumps he takes all over the place and goes around, etc., etc. Then you can look at his trail, the random walk trail. You can have 2 walkers starting off from the same point at t equal to 0 and taking random paths. They may or may not intersect each other. Okay? It turns out that in dimensions 1, they certainly will intersect each other, wait in long enough. In 2, they certainly will. In 3, there is a finite probability that they'll come and meet at some point. In 4 and higher dimensions, there is 0 probability that they'll meet. There are always sets of measure 0, but they don't intersect necessarily with certainty with probability 1.
And does this have anything to do with degrees of freedom?
No, it has to do with the dimensionality of space itself. It has to do with the dimensionality of space itself.
Because is it like because of the higher degrees of freedom of higher dimensional spaces?
Higher number of dimensions.
The
Degrees of freedom is a dynamical concept. It has to do with particles moving in a given force and so on. We are not talking about that. We are just talking about dimensionality of space. The number of coordinates needed to specify a point in the manifold.
So why do the walkers have to intersect in 2-dimensional space?
can we just
I'll prove that to you in the next time. I'll prove to you why in 2 dimensions you're guaranteed to meet.
So, but like, so something that is very basic for me, I think is, what if this walk off in the opposite directions like this?
You have to know average. No, these are all statements of average. The question is, you can have any two particular walkers will walk off the set of measure 0, right? You have to know average over all possible random walks and ask, is there a probability of the meeting or coming back to the origin or not? The statement is in 1 and 2 dimensions, the probability of a return to the origin is probability 1. There are always sets of measure 0 events where such walkers don't meet. But with probability 1, they will meet.
So it's like
Probability 1 doesn't mean certainly they'll meet. In mathematics and probability theory, probability 1 is called almost surely. Almost surely. Not surely. Almost surely. It's a very precise mathematical term. You see probability book saying AS after each equation, which means almost surely. That means with probability 1 in the sense in which we define probability. Number of successes divided by number of this thing, limit, etc., etc.
Limit tends to
And tends to infinity.
so it's like the possible the case where the two random walkers never meet each other. There's only one case. There's an infinite number of cases where they meet each other.
Yes,
So
yes, exactly.
so when we define that probability, because there's like the chance of them meeting is infinitely more than the chance of them
Yes.
not meeting. That's
Chance
why
of,
we have probability.
yes, that measure has probability 1, exactly. Except for sets of measure 0, that's the whole point. In 3 dimensions, it turns out that two random walkers starting from the same point will meet each other with a finite probability less than 1. But non-zero.
and in 4 dimensions.
In 4 dimensions, the probability is 0.
So there's an infinitely more number of times where they don't meet each other.
Yeah, exactly. 4 and higher dimensions.
So actually in chaos theory,
Yeah.
I think Professor Arun was talking about he was supposed to be talking about Mandelbrot set, but I don't know.
About what?
Mandelbrot set.
The Mandelbrot set. Yeah.
Yeah, he didn't have time. But sir, one thing I heard about Mandelbrot set is that it can also represent point dimensions like 1.8, 1.
Yeah, fractional dimension. They're called fractals. Yeah. Let me give you an example of a fractal set right away. This is something which all of you can easily appreciate. Let's start with a simple construction. And this will fix your mind for. Okay. This is called the Cantor middle third set. Have you heard of this? The Cantor set, the Cantor middle third set. So you take a line segment between 0 and 1. I take a line segment between 0 and 1, including the points 0 and 1. This is a compact set, it's bounded. It's also a closed set because the boundary points are included in the set. Right? And now I do the following construction. I remove the middle 1/3 open interval. So I remove this point. So this is 1/3, 2/3, and 1.
Now, do we have 1/3 and 2/3 closed in their own intervals?
1/3 and 2/3 still exist in the original set. I remove the open interval between 1/3 and 2/3. I erase it, I delete it. That's the first step. So I have a set now which consists of all points but no points lying between 1/3 and 2/3. The next step, I cancel the middle 1/3 of each of these guys once again. So I started with 0 to 1. And then 1/9 to 2/9 I remove, and 6/9 to 7/9 I remove. 7 to 8/9, sorry, I remove. Right? But all the other edge points I keep. I keep doing this. Are any points going to be left at all?
There will be an infinite.
How do I know there's an infinite number of points that are left?
You can do this operation countably infinite.
I have infinite patience. I do.
Sir, but at the end of the day, it's still countably infinite. You have one. Each operation.
Is it countably infinite? At the end of the day, do I get any points left, or do I get no points left at all? If I get any points? If you say there are points left, are they finite in number or infinite in number? Go, let it slowly. Is the number of points left 0 or non-zero? Is the number of points left finite or infinite?
Finite.
Finite or infinite? We have to do that. They are infinite. Are they countably infinite or non-countably infinite? Why do you say that? What's the length of what's left?
It's infinite.
What's the in the limit? What's the length of the step? The length, the total length of the step in the first step became 2/3. In the second step, it became 2/3 whole squared, which is 4 nines. So the length of this interval must go to this set must go to 0. Lebesgue measure is 0. So it's a dust, just a dust of points. Just a dust. But is this dust got a finite number of points or infinite number of points? Infinite. But is it countably infinite or non-countably infinite? Countably infinite. Let's see.
I think it's uncountable. Because you can still do one more of that operation again.
I do that in infinite number of times. So can I count the number of points on the interval from 0 to 1?
No.
Is it a countable infinity or non-countable infinity? Non-countable. It cannot be denumerated as 1, 2, 3, 4, etc., etc. Non-countable. But in the Cantor set, which is the limit set of this procedure, is the number of points infinitely countably infinite or uncountably infinite? The length is 0. Total length is 0. But I argue in the following way. Suppose I write any value of x as a decimal value between 0 and 1, but in ternary, not binary but ternary. So I use the symbols 1, 2 and 0, 1 and 2 to write it in ternary. So the initial point would have looked like this: 0.1, 2, 0, 1, 1, 2. All points in the first step here between 1/3 and 2/3 will start at the integer 0 or 1. Start at the value 0 or 0 point. Is it 0 or 1? It will start at 1. It will start at 1 and get, so that point, therefore when I delete this, all such decimals or ternary decimals will start at 1, 0.1 something, they are gone. Right? When I go here, the first decimal is either 0 or 2. And then everything that's got the middle value, which is 1, has gone. So everything with 0.10 is gone. Everything with 0.01 gone. 0.21 ... are gone. So all points which had 1 in the first decimal place are gone in the first shot. All points which had 1 in the second decimal place are gone in the second shot. Everything that has 1 in the third place is gone in the third shot. Finally, you are left with decimals which are either 0 or 2. But instead of 2, I could have called that 1. Just a label. So I have the set of decimals, set of numbers written in binary between 0 and 1. All numbers between 0 and 1 can be written in binary. So I have an infinite uncountable set of points. So the set has length 0, Lebesgue measure 0. It is just a dust, but it's an infinite set, and it is one-to-one mapping with the set of points between 0 and 1. Uncountably infinite. So you see, infinite sets are very strange objects.
So are there sets that are larger than this?
No, wait. Now you can ask, what's the dimensionality of this set? Topological dimension of 0 to 1 is 1. It's a one-dimensional line. If it's just a point, the dimensionality is 0. If it's a collection of points, the dimensionality is 0. But this guy is somewhere in between. Each time the scale is changing by a factor of 2/3. Right? So for reasons which I won't explain here, the dimensionality of the set is log 3 over log 2, which is a number between 0 and 1, which is a fraction. How is that possible?
How is it that we have like a fraction dimension, fraction dimension?
The topological dimension is still 0. The dimension as I defined, the fractal dimension, which I haven't defined, that is a fraction between 0 and 1. Okay? I have to define for you the fractal dimension. I'll do that sometime.
Can we say that this ultimately tends to a set where it's 1 by 3 power n, where n is some natural number, only those points are left behind?
Yeah, you can write down, no, but the infinite number of points. The points that remain can be put in one-to-one mapping with all the numbers between 0 and 1. They're not all rational numbers. They're mostly irrational. If I close my eyes and put an infinitely sharp pencil on the unit interval, will I hit a rational point or will I hit an irrational point? Yeah, I'll hit a rational point with some probability 0. They form a set of measure 0. It's a dense set. Arbitrarily close to every rational point, there are irrational points and so on, or vice versa. But the measure of the rational points on the line is actually 0. It's even stranger than that. The number of points, the quote unquote infinity of points on a unit square between 0 to 1 in x and y is the same infinity as between 0 to 1. Because you can do a one-to-one mapping. And it's the same infinity as the number of points in a cube of n infinite dimensions. Again, you can do a one-to-one mapping. So when you compare infinite sets, lots of strange things happen unless you're extremely careful.
So, is it like, I mean,
You should go on.
at least how I feel like I should understand the brackets that you just talked about. You said that the topologically from 0 to 1, we have a one-dimensional thing. As we reduce to a character set, we have like spaces that we don't need to define them. Like they're just empty. So in that case, it's possible for us to like cut down the dimensionality, for places we don't need to measure.
That's what is happening.
Yeah.
That's why it's no longer dimension 1.
Yeah.
You can't dissociate it dimension 1. It's not a continuous curve.
So take a random number of points which are in n dimensions, I get something of a fraction between n minus 1 and n.
Depends on the construction.
Yes, sir. Everything covers x, y,
Depends
z.
on the construction. Let's do it in 2 dimensions. And that's the Sierpinski triangle gasket that I mentioned once. That's got a dimension between 1 and 2. So his question is, if you have a fractal in n Euclidean dimensions, what is the dimensionality? It can be anywhere from 0 to n, in between, any fraction between that. Cannot exceed the Euclidean dimension, but it's anywhere in between, generally less than n.
So I have one doubt. So I've heard in like some places that fractals need not be self-similar.
Yeah.
But in this case, the way we're defining that dimension depends on self-similarity.
Yeah, this is completely self-similar because at any stage the same construction is applied over and over again. But if you look at a random walk, it is a self-similar walk, but it's not self-similar in the strict sense. But it is statistically self-similar. So there's a notion of statistical self-similarity which is not exact self-similarity. And that's the most useful one. Okay. Biology transcends everything else. We need to go and eat. Okay, next time. Until next time.
Swayam Prabha. Digital India. Educated India.